So let's go through a couple of examples on two population proportion questions. First one says an insurance company wants to offer discounts on its life insurance policy to non-smokers. So for part of the analysis, the company randomly selected 200 men and women who are 50 years old and asked them if they smoke and if they've ever had heart disease. The results indicate 20 out of 80 smokers and 15 out of 120 non-smokers suffered from heart disease. At the 5% level of significance, can we conclude smokers have a higher incidence of heart disease than non-smokers? So one of the things you might want to do first is define your P1 and P2. We know we'll have two Ps because it's a two population proportion. What should we call P1? And we got to say more than just smokers, because smokers isn't going to give me the proportion. P1 can be the proportion of smokers who have heart disease, right? And then likewise, P2 will be the proportion of non-smokers with heart disease. And from that, I can define my HO and HA. In this case, HO, the hypothesis of no change or no difference, is that those two things are equal. HA, smokers have a higher risk. Sometimes I have students who put hats on top of HO and HA. You don't need to do that. How come? There's p-hats later in the problem, and I wouldn't need to do a statistical test to know if those p-hats that are going to show up later in the problem are equal to each other. I mean, my second grader could figure out if they're equal to each other. There's the two numbers. Are they equal to each other? This says, are the true proportions equal to each other? From here, we've got to go to step 2, which is to do what? State your assumptions or your condition. We know that we need an SRS and we need independence. Since it doesn't address it more than just saying randomly, we assume the two groups are independent SRSs. I am certain there are more than, you could either write 10 times 80 or you could write 800 smokers and 10 times 120 non-smokers. Thankfully, there are more than 5 successes and failures in each group. And then I'm going to list those out so somebody believes that I actually checked it. I looked at those numbers right there, and that's the 20 and 15, and then I subtracted to get the 60 and 105. Now, before I move on, I want to talk real briefly about what each of these things allows me to do. What does independent allow me to do? To add the variances. Okay, it allows me to add the variances from stuff we talked about in Chapter 7. What does SRS help me avoid? Bias. What does the fact that there's more than 800 smokers and 1,200 non-smokers let me do? It lets, this one's a little tougher. It lets me use this kind of formula as a pretty good estimate for the true standard deviation. And finally, what does it help me do that there's more than 5 successes and failures in each group? That's the one that says I've done it enough times to get a lot of yeses and a lot of nos. What does doing something enough times help me with? Getting a normal sampling distribution. So that's how each of those figures into the problem. What's step 3? Do your calculations. So let's write it out. Z equals P hat 1 minus P hat 2 minus P1 minus P2 over the big standard deviation, or the big square root of P hat 1 minus P hat over N1. And this is the pooled P hat that I'm using here underneath the radical. I'm hopeful that after you've written this a dozen times or so, it ought to sort of flow off your pencil when you're writing it. Because when you have to stop and think about that formula, that's when you run the risk of screwing it up. So now let's plug in the numbers. So P hat 1 was 20 over 80. P hat 2 was 15 over 120. Minus, what's P1 minus P2? 0 over big square root. Now, how many people had heart disease? Now, that's how many people I sampled. 35 of them had heart disease out of the 200 that I sampled. And this is 1 minus 35 over 200 over the number of smokers plus the same thing, this pooled P hat, counting everybody in the same group, over the number of non-smokers. Now, of course, we're not required to do all this the long way, but we can use our calculators to go stat test 2 prop z test. That's 2 proportion z test. And type in your data here, 20, 80, 15, and 105. One-sided greater than test. Calculate. Where were? I think I made a mistake somewhere. I must have typed something in wrong. Hang on. 2 prop z test. This is 120. Sorry, 120. Calculate. There we go. That looks more familiar. And so that equals 2.28, giving me a p-value of 0.0113. Now with that little old tiny p-value, what do I do? Reject HO. So I'll use green. Since my p-value is so small, and by small was defined in this problem as being 5%, a 5% level of significance. I will reject HO in favor of HA. I now believe smokers develop heart disease at a higher rate than non-smokers. Now, I think there's a very logical question that comes from that conclusion. And that very logical question can be answered by doing a 2 prop z int. All the stuff is still there. I'll turn this into a 90% interval. What very logical question from that conclusion is answered by that confidence interval? Yeah, how much more? What's the rate that's different? I just told you I thought it was a different rate. How much more do you think it is? I don't really know, but I think how much it is a number that's somewhere between 3 and 22%. That's what I would get from the confidence interval, how much higher it is. So based on what we just did, would it be a legitimate conclusion to say smoking causes heart disease? No, why not? Because that's causation, and this was not an experiment, it was an observational study. So we found a connection, an association, a link between smoking and heart disease. That's different than saying smoking causes heart disease. Now, don't take this to the wrong extreme. I'm not saying that smoking doesn't cause heart disease. It might cause heart disease. I'm just saying that this information doesn't show me its causal relationship. To determine the causation, I would need to impose the treatment, require some smoking of people. Number two, then, two competing drugs are available for treating a specific ailment. There are no apparent side effects from drug one, but there are from drug two. A group of researchers has decided that they're willing to recommend drug two if the proportion of cures affected by the second drug are higher than that of the first drug. The researchers used the drugs experimentally on two groups of people who were suffering from the ailment. By the end of the experiment, 52 out of 80 with drug one were cured, whereas 63 out of 90 given drug two were called cured. At the 1% level, should the second drug be recommended? Now, I think that reading this with a pen is a good idea, but simply underlining certain things is not the same thing as writing it in your answer. So sometimes it may say random somewhere and somebody wants to circle it and say, I told you it was random because I circled it. My response is, no, I told you it was random. I want you to make sure that you've reiterated that to me. So writing the P1 and P2, P1 is going to be the percent of people cured by drug one. And P2 is the percent of people cured by drug number two. So HO is that the drugs are equally effective. HA is what? This is a little bit of a trick you got to be careful of, I think, because it says the second drug is higher, but you actually draw a less than sign because the second drug is what's listed second. So be sure your inequality is facing the correct way. But it is a one-sided test. And now I can do my conditions. So I'm going to write up the conditions. If you're watching this, you can pause it and copy down what I wrote if you're interested. So since those conditions are met, I'm going to do the two sample procedures for the difference in proportions. And I will write up my formula. Z equals P hat 1 minus P hat 2 minus P1 minus P2 over the big square root of the pooled P hat 1 minus P hat over N1 plus the pooled P hat 1 minus P hat over N2. Now I'm going to work this one a little bit differently than I did before just to show you a variety. It is permissible at this point to write this. Let's get my givens again. Now I've written the formula and I've written all of the numbers that should be plugged into the formula. A good algebra student could take what I've written on the right and plug it into the formula on the left. I need not rewrite the formula with those things plugged in. So you can do it like I did with this problem, or you can do it like I did with this problem. It doesn't matter to me. It doesn't matter to the AP people. Pick whichever way you like. And then in either case, you're going to actually grab your calculator and go to prop Z test, 52, 80, 63, 90, one-sided less than, calculate. My Z test statistic is negative 0.6956. So this p-value is pretty big. And since my p-value is so big, In other words, 0.243 is greater than my significance level, I fail to reject HO. I am unconvinced that drug number 2 works better than drug number 1. And I wouldn't do a confidence interval right here at this point to find out how much better it works, because I just told you I'm not convinced that it works better at all. So it would be foolish for me to go ahead and find a confidence interval about how much better it works. So question 3 is a little bit different. There's a wrinkle here in question 3. So I want you to read question 3 and we'll talk it through.